All right, chapter 5 of our exciting saga, Econometrics and You. I've been looking forward to this chapter. All right, we're finally going to be able to do t-tests, and that's going to be something that you'll be using in the homework for the rest of the semester, and perhaps for the rest of your life. All right, let's see here. Now, it's one thing to say that in our regression here, grade is equal to, let's say we estimated 14.2 plus 7.9 times hours. It's one thing to say that you did your estimate and got those numbers, but it's another thing to say, yeah, but are those statistically significant? The computer is going to give you a number. You asked it to give you a number. It's going to do its best to figure out what the relationship was between hours and grade, but can it vouch for that number? Can it say, yeah, actually, I'm pretty dang sure that's the right thing? It's just like I gave you this example, I think maybe in chapter 2, and okay, you run a casino, and you've got some game at the casino where a person flips a coin and has to guess what whether there's going to be heads or tails. And somebody's winning a whole lot more often than you think makes sense. So you have this person dragged to your office and you say, I think you're using an unfairly weighted coin. I think your coin is unfairly weighted towards heads. And I'm going to have one of my assistants here flip this coin 100 times. And if we determine that it is unfairly weighted towards heads, then we're going to kill you. All right, so it's a very exciting story. So let's say they flip it, and they get 51 heads and 49 tails. Did you get more heads than tails? Yeah. Is it statistically significant? No. Sheer chance you could end up with that, right? I mean, you could easily end up with 51-49, and let's not kill the guy. Or 95 and 5, did you get more heads than tails? Yeah. Is it unfairly weighted? Yeah, it is. I mean, that's clearly, this is not random anymore. That statistically speaking, we have a pretty high level of confidence that this is an unfairly weighted coin. That's what we're after in this chapter. We're after this part. We're after saying, yeah, I got 7.9, but how close was how close were the points to the line? And so we're going to use t-tests for that. All right, let's see what I got here, John. Most common use of econometrics, develop hypotheses. All right. Oh, it says here, tossing a coin example again. I already did that. All right. 3 basic. Okay. There are 3 basic hypotheses that we'll be making about the parameters, about these numbers. Now, as I just told you in the previous chapter, whatever. We can still do it for the intercept. We can still do a t-test for the intercept, but we rarely care that much about the intercept. What we usually care about are the slope coefficients, the beta sub 1, beta sub 2, beta sub 3, and so on. And so there are 3 basic hypotheses you can make about a coefficient. And remember this, by the way, from let me go back to a previous chapter here. No, I didn't. Chapter 3. Remember the steps of doing a regression analysis? And look down there at number 3. That's what we're about to talk about. We're about to talk about the assumption you make regarding the signs of the coefficients. You could assume that a variable is going to be, or hypothesize, I should say, positive, negative, or simply, in fact, let me change those to significant. You can hypothesize that a variable is going to be positive and significant, negative and significant, or just it's going to be, I don't know what sign it's going to be, right? And I'm going to go over this one time, but we're not really going to use it a lot more after this. But I'm going to go ahead and use the sort of formal method of setting this up because he does so in the book, all right? So I'm going to give you a formal way of making these 3 hypotheses here. Although generally speaking, after this chapter is done, we're never going to do it this way again. All right? But he's trying to give it to you in the more formal way first, and then we'll just sort of do it quick and easy after that. All right, so here's the one where you think the variable is going to be positive. For example, like hours of study. You're going to hypothesize, well, that's got a positive impact on the dependent variable. See what I got here, John? Beta is for each of the coefficients, we're making a hypothesis like this. We have a null hypothesis and an alternative hypothesis. Let me write that out over here. Null and alternative hypothesis. Okay, the null is actually what we don't think is true. All right, the null is what we don't think is true. So it's like saying, well, very much like saying that you're the district attorney and you're trying not a client. What do you try? A person. And the null hypothesis in the court of law is that they're innocent. All right, that's the null hypothesis. That we assume they are innocent until we prove them guilty, all right? So the null is the innocent. The null is, if we don't even attempt to try you, you're innocent. We assume you're innocent by default. It is the null hypothesis. It is a burden upon us to prove that you are guilty. So the alternative is actually what you really think. The alternative is, I believe it's a positive impact. I believe that when we run this regression, we're going to discover that grade equals an intercept plus some positive number, you know, on hours. All right, next one. Null hypothesis. Beta is greater than or equal to 0. Alternative hypothesis is actually what you think. Oh, I'm sorry, I left the beta off. Is actually what you think is really true. What you think is really true. And then let me draw the last one. I shall use green. Now you might be wondering, what the heck am I going to write down for the null and alternative hypotheses here? Because over here, it's like, well, it was going to be less than 0. It was going to be greater than 0. What am I going to do over here? I don't know if it's going to be positive or negative, but it's not going to be 0, all right? In other words, it's not going to be totally irrelevant. What if you ended up with grade is equal to 14 plus 0 times hours of study? Well, then it's irrelevant. Hours of study are totally and completely irrelevant, all right? So in the case where you don't know whether it's going to be a positive or negative impact, which would not be true here, but positive or negative impact, your null is that it's 0. Your null is that, hey, I could be wrong. And so the burden is on me to prove it is not 0. Now, I can prove it is not 0, either positive or negative. Over here, you're saying, I believe the impact is negative. Let's say down here we have, okay, number of absences, all right? We'll add in number of absences down here, and you say, well, I think that's going to have a negative impact, all right? So if I get a positive number or something that is insignificant, then I haven't proven my case. All right, let's see. Am I ready to move on to how we actually use this? Yeah. Now, here's the thing. In terms of trying to prove your case, I know, go back to this. Going back to the example of tossing the coin. We knew that 51-49 was certainly not enough to prove that it was unfairly weighted towards heads. 95-5, I'm pretty darn sure, is significant in terms of it's unfairly weighted towards heads. But where is the cutoff? Where should the cutoff be for Is it 90? If I get 90-10, is that enough to say that it's unfairly weighted? And obviously that is a judgment call. There is no answer in nature on where you draw that line. But inevitably there are two potential errors you could make. One is, and let's see which way what order he puts them in here. Yeah, rejecting the null when it's true and not rejecting when it's false. There are always two possible errors, right? You could reject the null hypothesis when it's really true. Or you could not reject it when in fact it was false. Those are the two kinds of errors you can make. I assume that's type 1 and that's type 2. I can never remember which one is which, but since they were written in that order in the book, I'm guessing that one's type 1 and that one's type 2. But it doesn't matter. You don't need to know which one is type 1 and type 2. All you need to know is that there are two potential errors. Think back to a court case. The two potential errors are that I could put an innocent person in jail. The null hypothesis is that they're innocent, right? I could reject the null hypothesis when it was true. That's one mistake you can make in court. You can convict an innocent person, and that's the first one, convicting an innocent person. You rejected the null hypothesis of innocence when in fact they were innocent. That's one possible error, right? The other one is that you could not reject innocence when in fact they were guilty, all right? And no matter what you do, those two possible errors still exist in a court of law. Those two are always there. It's always possible that you convict an innocent person or let a guilty person go free. And where you draw the line on the weight of evidence necessary to reject the null hypothesis will only change the likelihood of these two. It will not eliminate them, all right? So and what we have opted for in our own court system is that we would prefer that we let a guilty person go free than accidentally jail an innocent person. So we have drawn the line to where you're going to have a whole lot of evidence. All right, you have to have a whole lot of evidence to reject the null hypothesis. You have to be, and what is it? It's not incontrovertible evidence, but you know, the bulk of the evidence, it must be clear. We try to make it hard to reject the null hypothesis in an American court of law. We, once again, would much prefer that we accidentally let a guilty person go free than put an innocent person in jail. So where we drew the line has attempted to minimize this risk. And we want to make sure we don't put an innocent person in jail, but then that makes this risk bigger. When you make one smaller, you make the other one bigger. What if we went this way instead? What if we went like, you know, any slight evidence is enough to convict you? We're going to have a whole lot of innocent people in jail, but pretty much all the criminals will all be there too, right? Because we will have made it very easy to convict somebody. You make it hard to convict somebody, you're going to have very few innocent people in jail, but you have a lot of criminals walking free, all right? So, and that is, again, as I was saying over here, it is not something that we can decide in nature. There is nothing to tell us, well, it should be exactly like this. It's a judgment call. All right. So, having said that, what we basically decide in economics is that, for the most part, we have to be 90% sure to reject the null. All right. We stack the deck against ourselves. That we've got to be 90% sure that that's not true in order to reject it. We want to believe this, right? This is what we want. We set this whole thing up to try to discover if this was true. This is the absences in class. This is the hours of study. We're hoping that our regression analysis shows that we rejected this or rejected this so that we can have this one, because that's what we put the paper together for. We wanted to show, yep, sure enough, skipping class hurts your grade. Or, yep, sure enough, studying helps your grade. So, but in order to be good scientists, we stack the deck against ourselves. We insist on at least 90% likelihood. I'll show you what that translates into when we get around to the T table here in a minute. All right, let's see. Should I go ahead and show them that now? Yeah, okay, I will. No, I think I'll actually go in a different order than the guy has it in the book. Yeah, I think I'll do it this way instead. All right. What you end up generating when you run a regression is something called a t-score for the individual parameters. So let's go back to, there we go. Let's go back to the whole grade thing. Grade is equal to 14 plus, I don't know. Oh, I want to make this an easy number to divide into. 10 times hours. You ran your regression and you got that. All right, you got a 10 for hours. And you're like, okay, my regression suggests that for every extra hour of study, a person gets a 10-point higher grade on the exam. But how confident are we that that's true? Here's the way we figure it out. There is a standard error for that variable right there. The standard error of, did I put a hat over that? Yeah. Oh, I'm sorry, that should be sub 1. It's very simple, all right? The standard error is how wrong this was on average over all the observations, all right? How far off was this on average? What was the standard error? What was the standard amount by which it was wrong? Check this out. Hours, grade, a pretty steep line there. There's 14 right down here. Yep. And here is, of course, grade equal to 14 plus 10 times hours. And I put a hat over it because that's the line. The hat's the line. But the actual observations may not be on the line, all right? Well, in fact, they're not going to be, are they? So let's say that the actual observations are represented by these blue dots, right? As opposed to these red dots, which I'm trying to make still on average on the black line, but further away. See how well you can see that? All right, so the blue dots are much closer to the black line than the red dots are, and yet they still have a slope of 10, each of them. Like, let's assume that's true. They still both have a slope of 10. Well, the standard error of the blue points, the amount by which on average it was wrong, it wasn't on the line, and this is in absolute value terms, of course. Otherwise, on average, it would be 0. But on average, the amount by which it was wrong, let's say that amount on the blue one was 2, all right? Versus on the red one, let's say, was 5. Maybe on average, the red one's off by 5, all right? We get a t-score out of this. The t-score is t for the kth variable. I'm sorry, yeah, that's right. T for the kth variable is, yeah, I want to do it that way. That's not quite right because it's really this minus 0, but don't worry about that. It will almost, I think once in my career I have had to run a hypothesis that was different from this, but it's almost always this. So you can read about it in the book, but I'm trying to stick to stuff that's most helpful to you. So this t-score is going to be this. It's the estimate of the number divided by its standard error. So on the blue line, that's going to be 10 divided by 2. So the t-score for beta sub 1 is going to be 10 divided by 2. It's going to be 5. The t-score for the red is going to be 10 divided by 5 is going to be 2. All right. Notice, first of all, that the t-score for the one we know is better is a bigger number. And that is generally true. Well, not generally true, it's always true. That the bigger you're hoping for big t values, right? Now, the t-values can also be negative because the coefficient can be negative, but I mean large in absolute value terms. So you're hoping for large t-scores. You're hoping for that because then that means that, wow, not only is it 10, but hey, that was pretty darn close all the time. On average, it was pretty darn close. On the red one, because the average error was bigger, we ended up with a smaller t-score. And that's actually probably still going to be significant, but anyway. So what we do now is, all right, after you have, and the computer does this automatically, obviously, the computer will be spitting out a number for the coefficient, it will spit out a number for the standard error, and it will automatically spit out a number for the t-score. You now compare the t-score to a table that's in the front page, inside front cover of the book. That's how important it is. That's how often you're going to need it. It's on the inside front cover of the book, but it's also on page, and I'm going to mention this too for a reason I shall make obvious in just a moment. It's also in the back of the book. Okay, here it is. B4, B1, B2, here it is. Page 518. 518 has it repeated. Plus on 518, they explain again how to do the test. That's really handy. And that's something else that this book does right. A lot of your econometrics books, they just have that, right? And they expect you to look back in the book to remember how to do the test. He always reminds you, right before the test, before the table, I should say, hey, here's how you do it. I'm not going to make you go back and reread the chapter. Here's how you do it. It's really handy. I love this book. All right. So we would get our t-score. We would compare it to a critical t-value. T sub c. And now, I believe I'm going to have to fill in the gaps that I skipped over a minute ago. But let me just tell you, let me show you this up close. Oh, let me do the inside front cover one actually. See all those numbers on there? That's what you would compare the t-score. For example, take this one, say right over in here. Say that was the one that ended up being our critical t-value for this study, 2.048. If it was 2.048, this would pass, this would fail. We would be unable to reject the null hypothesis that in fact this might as well be 0. I'm going to say it again. If our critical t-value were 2.048, and again, I'm going to have to go back now and fill in some gaps on why would we pick that particular number. If it were 2.048, this passes, this does not. All right, this number is too small. This passes. We reject the null hypothesis, and we are able to accept the alternative hypothesis that this is a significant number here, a significant in terms of statistically significant. 10 was pretty close to how much it did add to people's scores. With the 2, now it's barely insignificant, which would be horrifying, by the way, if you were running this regression. You're like, crap, it was so close. But it didn't make it. So you have to say, well, I got a 10, but it's not really significant. All right? It's not statistically significant. We don't have a lot of confidence in the fact that it came out with a 10. When the t-score was 5, we have a lot of confidence in this 10. When the t-score was 2, we don't have a lot of confidence in it. All right, so you're going to be doing these t-tests all the time. Now let me backfill some of the things I skipped over so that you can see why we would pick the particular numbers we would on that table. All right, now, and I do think this, I think I like this order of doing things better than what I was going to do based on my notes in the chapter. Here's the deal. All right, let's stick with that example. All right, imagine all the t-scores that you could possibly generate in taking samples. I'm thinking of that measuring cup again, dipping it in there and getting out samples of hours and grades, all right? Think of all the various t-scores you could generate by doing that, all the samples. And let me see if they have a chart for that actually. Or oh wait, I think I do actually. I've already gone past that page. Ah, here it is, here it is, okay. Yeah. These will be, oh shucks, I didn't put down which table they are. Figures. Here they are. 5.4. Okay, 5.4. Now, oh no, I don't want to do it like that. T-scores can vary from 0 to, well, I guess positive infinity and negative infinity. And so there's a whole range of t-scores you could possibly get. Once again, be thinking about taking random samples out of that big drum, out of that big oil barrel. Now, given that, when we look up on a table for a critical t-value, we're looking for a cutoff point. We're looking for a point at which we would say, if we get a t-value that's greater, and that example I did a second ago, that was 2.048, right? So that would be our value right there. So if we get a t-score bigger than 2.048, yes. If we get one equal to or less than, you cannot reject the null hypothesis. So this table gives you all the critical t-values. Again, I'll tell you which number to use here in just a minute. But this is what it's basically doing. It's imagining all the possible t-scores that could possibly be generated. And these are going to vary from 0 to, infinity in either direction. A one-sided t-test cuts off, remember I said at least 10%? It has to be at least 10%? A one-sided t-test cuts off 10% of the area underneath this curve to the right if it's a positive number, and then flip this thing over, imagine it flipped over, to the left if it's a negative number. Now, if it's that very unusual situation of, I think it's significant, but I don't know if it's going to be positive or negative. What was it I'd been using before in class? I think it was cups of coffee. Cups of coffee could go either way. Either it stimulated you enough to do well on the exam, or it could be that you have to go to the bathroom, you can't concentrate, and the caffeine is getting to you. It's also a depressant. So I think cups of coffee are significant, but I'm not sure if they're positive or negative. So I want to put that in. In that case, the 10% is cut off like this. And that's a two-sided t-test. On a two-sided t-test, any t-value you get, including the critical value from here to here, is, well, crap, I didn't reject it. I guess I'll draw one for the absences as well. All right. We'll do a bunch of examples of this. And let's see. Now, we don't have to use 10% as the cutoff point. I'm using it as an example right here because it is essentially the least we'll allow. All right, it's going to be we could do 5%, we could do 1%, but generally 10% is the sort of, we wouldn't have 20% significance value. That wouldn't be acceptable in an economics article, economics journal. So 10% is usually the, I'm stuck between saying highest and lowest here. That it's got to be at least 10%. I'll give it to you in a minute. I'm struggling between describing it as least or most, because of course the problem is that 10% is 90%. So let me word it that way, which feels better. We're 90% certain this is true. We're 90% certain. We're 90% certain. And so 90% is the lowest we'll go. We can't be 85%. We can't be 80%. We can't be 70%. It's got to be at least 90%. And 90%, what's that? It's cutting it off to where there's only 10% left, that you really got to prove your case. You've really got to make sure that people, that the statistics are on your side. All right, so let's see. Now what do I want to do next? Page 25, the dog is barking. I believe the male employee is here. Ooh, I don't want to forget to tell you that, but I don't want to bring it up right now. And am I getting up on 30 minutes? I am. All right, so let's stop and start again. Let me cut this off at 30.